Good morning, everybody. My name is Philip Gardiff, and it's my pleasure to introduce our second keynote speaker, Dr. Jennifer Keenahan. Jennifer is a colleague of mine in University College Dublin, where she works in the Department of Civil Engineering, working on combining experimental and numerical methods to analyze various flow phenomena, in particular the built environment, fire and smoke modeling, and building on her industrial experience in Ireland. So please join me in welcoming our next keynote speaker.
Okay, hello, it's great to be here. So I want to start off today telling a short story. Some of you might know this story, some of you may not. This is a video from 1940 of the Tacoma Narrows bridge disaster. So as you can see in the video, the bridge is swinging and twisting pretty violently. You can see in this clip, the rotations are quite severe. The lampposts are swinging quite violently. So this is one of the most famous bridge collapses and bridge disasters. And what caused this was interaction with the wind environment. It wasn't a particularly high-speed wind that caused this. It was a relatively low wind speed, but the interaction of the wind with the bridge, the dynamic interaction, ultimately caused the collapse. And this was a pivotal moment because before this, wind dynamic interaction didn't really feature in the design of bridges. And since then, since the 1940s, it has become an important discipline. Having said that, we are still having, to this day, challenges with wind-bridge dynamic interaction. So this is the Humen Pearl Bridge just outside Hong Kong. This was recorded in May 2020. So you can see this bouncing of the bridge, bouncing of the traffic. It's quite alarming, really. So it's a very poorly understood area. And part of that challenge is that it is very multidisciplinary. It is at the center of fluid dynamics, fluid mechanics, structural dynamics and structural engineering, meteorology and the wind climate, the coupling and dynamic coupling of systems, and invariably probabilistic methods. Because in design, in civil engineering design, we design for a probability of something occurring or not. So it's a very multidisciplinary problem. So for those of you who don't know me, I'm Jennifer. I'm from University College Dublin, and I'm particularly interested in this subject of bridges and wind and their dynamic interaction and the coupling and the problems that can occur. And there's a couple of very unique features of this problem. Structures, the built environment, is in the atmospheric boundary layer. So everything in our world, in our built environment, is exposed to extremely high turbulence, so extremely high Reynolds number flows. And bluff body aerodynamics as a subject is not very well understood. It involves the separation of flows and the reattachment of flows to large structures. And the bit that's not widely known is that bridges are always moving. So whether we can see it or not with our eyes, bridge dynamics an ever-present feature. Bridges are always moving. So there's a couple of features then. There's a couple of interesting phenomena that occur when we analyze, when we look at a flow around a bridge. So we have the oncoming turbulence. So there's an inherent turbulence in the natural wind. We have flow separation occurring when it interacts the bluff body, the bridge. And then we can have this vortex shedding feature in the wake. And where this all becomes complex is when we look at these sources of the aerodynamic forces that act on bridges. So the wind loading, these aerodynamic loads, these forces, generally come from three key sources. The first being the natural wind and the buffeting or the drag forces that occur on the bridge. The second source of force is due to the separation and reattachment of and the vortex shedding that occurs. And then the third one is when the bridge itself, the structure itself, is moving. And then we move into this aeroelastic behavior where the wind is exciting the bridge and the bridge is exciting the wind, and the whole thing becomes very iterative and interactive. So this illustration kind of helps understand a little bit. So we can have these extreme wind events with bridges where the flow features, the attachment, the separation, the reattachment, the vortex shedding, where that results in forces that cause the bridge to move way in excess of what it might have done. And this invariably leads to a number of instabilities. So the galloping instability is one-dimensional. It's that kind of bouncing that you saw in the video, and that generally occurs in high-speed flows, in high winds. Flutter then is what we call the two-dimensional version, again in high-speed winds, and we'll have a rotation effect there. And that is what is recognized as having caused the collapse of the Tacoma Narrows Bridge. The third type of instability then is what we call vortex-induced vibrations. This tends to happen at very low wind speeds. And so it's not as simple as designing for the speed of the wind. It is much more complicated. These instabilities can happen in very low wind conditions. And then a more recently recognized phenomena or instability is that of rain-wind induced vibrations of the cables. So this is relevant to this particular type of bridges that involve cables. So this is a picture of a wind tunnel, and wind tunnels are typically what we use to assess a bridge structure before it's built, or indeed if it's experiencing problems in operation, we may come to the wind tunnel for some analysis. So this is the state of the art. This is what is done in practice. And this is what is accepted by the codes of practice. But there's quite a number of inherent limitations to wind tunnel testing. The bridge is a scaled model. So there are inherent violations of the Reynolds number when we scale the geometry down and we then have to scale the speed of the flow. We need to decide ahead of time where to put the sensors. And we're hoping that those sensors won't disrupt the flow and upset the measurements that we would take. And then we'll only ever have information at those discrete points measured by the sensors. So there's quite a number of limitations in the use of wind tunnel testing. So you might wonder, it's been 10 minutes, what am I doing here at the OpenFOAM conference if I'm talking about bridges and wind? So I am particularly interested in the numerical modeling, the computational modeling of this problem. So this is Shuzo Murakami. He's recognized as being the godfather of computational wind engineering. It's as a subject only been around for about 30 years. And he pioneered the first conference in this space. But there are very few people that are interested in computational wind engineering that are also looking at bridges. It's a poorly studied area. And I mentioned quite a bit already about the design of bridges and making sure that we're not going to have these structures that might collapse. But when the bridge is in operation, we want to be sure that vehicles won't turn over because of high winds, so that the operational aspects of the bridge are also considered. And this is where OpenFOAM as a tool becomes really powerful and really important. So I'm going to mention two specific bridges today that I'm studying. The first one is the Rose Fitzgerald Kennedy Bridge in Ireland. It was constructed between 2018 and then eventually opened in 2020. And 9 days after it was opened, it was closed again because there was a storm coming and the operators were not sure if it would be safe to keep open. So they closed the bridge. It was opened again a couple of days later, but it's a little bit embarrassing to not have a good understanding of this problem, that we can't have confidence in keeping this infrastructure in use. So fortunately, I have access to the wind tunnel testing reports that were prepared for this project. And what's particularly interesting, if you see in that picture of the third report, that is the model truck vehicle that was used in the wind tunnel. It's made of little bits of matchstick and chipboard glued together. So, you know, that's a further indication of the limitations of wind tunnel testing. The vehicle in these tests is stationary, it's not moving, and its geometry is quite limited. But in addition to having these wind tunnel reports, this bridge has been instrumented with sensors, lots of sensors. And the points that you can see there, A, B, C, and D, are the locations of the anemometers that are measuring the weather data. So there's an ongoing recording, monitoring of the wind speeds, the forces, the strains, the displacements that are occurring on this bridge. And that offers a very useful source of validating potential computational models, which brings me to the purpose of my talk today and validation of models and the importance of it and the opportunities we have with it. So this is a schematic of where I'm trying to get to. So I'm looking to analyze the dynamic coupling of vehicles traveling at speed on dynamic bridges, experiencing high winds, which is not an easy problem to solve. But I think it's extremely important, not just for the design of the bridge, but also for the safe operation of the bridge. Cognizant of the fact that we are in a climate emergency and that the wind speeds that we might experience today could be vastly different from what we might experience in a couple of years. So this is a an image of the mesh for the model for that bridge. It's got a very, very large number of cells. The modeling process has taken 2 phases. The first is where we modeled at the wind tunnel scale to see if we could achieve similar results to what they did. And then we moved to full scale, where we modeled the true geometry and the true dimensions of the bridge. And for those that are interested, the full details are in the publication listed on the bottom of the screen. So a really important feature of the modeling is the accurate modeling of the inflow conditions, that we are prescribing the wind as it truly was, or is, or will be. So for that, I worked with a meteorologist in University College Dublin, and they ran the climate studies, the weather forecasting models that they use. And we mapped from their model to my model the inflow conditions. We have done this for RANS simulations. It's a vastly more complicated thing to do for LES. And that's a feature of the ongoing work I have in this space. The initial results that we have, however, are really promising. So what you're seeing on the screen now is for one of the sensors, sensor C, that you can see on the top diagram. The red curve is what we got from our CFD model at this location C. The blue is the 10-minute average of the sensor data, and the green is the raw sensor data. So we are certainly in the right ballpark in what we're doing. And it's very encouraging to see that the simulations we've been able to produce are quite accurately representing what's happening in reality. When we compare that to the wind tunnel report, we see quite a lot of difference. So what we're looking at here are the drag forces, as distinct from the previous slide, which had velocities. So the yellow color squares along the top are the drag forces estimated by the Eurocodes. This is what we would design to in practice. So you can see there's an element of conservatism there. There's quite a big difference between what the wind tunnels would report and then what our CFD simulations have found, and indeed different again to the sensors and what they can capture. So there's certainly a lot of room for further investigation to truly understand what do we take as the true data. And the true data, of course, is the field measurements. And then how good an approximation are the wind tunnels, and how good an approximation can we get from the numerical simulations. So this is the second bridge that I wanted to talk about. This is the Queensferry Crossing. So this is in Scotland, and it was opened at around the same time in 2020. It cost something like £1 billion sterling, and it was a 10-year-long project. So much so that I was working for the company who built the project, who built the bridge many number of years before I came back to academia. So similarly, it is similar to the Irish bridge. We have a suite of wind tunnel test reports for this bridge that were prepared and done before it was built. Interestingly, they were done in the wind tunnel in Polytechnic di Milano, which is not far from here. And I have some students that are looking at this as well. So we've developed a very comprehensive model with an enormous number of cells to try and make sure that we are capturing the flow interaction close to the structure, which is extremely important. And there are some initial results and details of the modeling in the publication listed on the bottom of the screen. And one of the things that became quite tedious in this modeling was looking at the different directions of the wind. So we don't just look at the prevailing wind conditions, we consider north, south, east, and west at a minimum, and perhaps northeast, southwest, and so on. So every time we change the inlet, we need to change our mesh. This becomes extremely tedious when you're dealing with a large mesh. So this idea came from one of my students, and they suggested that we put together a cylindrical domain instead of a square domain or others. And he tested this, and he found that it vastly improved his efficiency of his simulations. And the results are comparable. So here we're seeing in red the 5-minute average of the sensor data. In blue, the results from the cylindrical domain. And in green, the equivalent results from the cube domain, the square one. So again, quite encouraging. So this is only, in my mind, the start of the process. I want to move to LES simulations for many reasons, specifically because they capture the variation in time that we can't get from a steady analysis. And as engineers, as designers, we are particularly concerned with peak pressures as opposed to time averaged pressures. We can really only get those from an LES simulation. But furthermore, I want to go to fluid structure interaction. I want to mesh the structure as well as the fluid. I want to capture the dynamic coupling. So these are all questions that I have, and I would be delighted to speak to anyone here today that might be trying something similar in OpenFOAM, or who might have done something similar, or who might like to have a chat. And just before I finish, there's 3 other ideas I want to mention. So colleagues of mine have come to me with ideas, and I find it hard to say no. So I say, yes, okay, we'll do some simulations. So one of these topics is on de-risking the site selection for offshore renewable energy. So we have a big mandate in Ireland to increase the amount of offshore renewable energy that we are developing. And the only wind farm that we have constructed to date had scour issues, erosion of the turbine foundations, which is a major problem. So we are looking at simulating the movement of sand particles on the seabed under a current, a flow, to assess whether this erosion will happen. So some preliminary results are there on the right, where we have successfully correlated the shear stress experienced by the seabed with the data that we've been able to collect from repeat surveys of that site. And we're currently developing some experimental simulations in the flume in UCD to further validate this work. So I suppose the purpose of me mentioning this today is to tie in with the topic of the talk, which is on validation and the opportunities and the importance for validating our simulations. In keeping with that, is another student of mine looking at the flow patterns in water treatment facilities and how we can optimize the flow path, the treatment efficiency in these tanks, whether we can change the geometry, change the porous media, include baffles, and so on. So we've started to create some simulations, and we're validating them with some experiments in the lab, which you can see in the photo on the left. And then the final one, and this is also a pitch for the session tomorrow. So my student Shihang is presenting his work tomorrow. And this is looking at eco-engineered sea defenses and whether we can modify the types of sea defenses that we use instead of these large concrete boulders that have an enormous embodied carbon, whether we can use an eco-engineered sea defense that would be more environmentally friendly, more sustainable, and more friendly to the biodiversity that we're trying to cultivate, and whether we can use these eco sea defenses and that they would perform as well, that they would dissipate the energy of the waves as well as the other types. So I'm conscious of time and that we were running a little bit late, so I'm going to stop there. I'd invite you to connect with me online. Come and find me at the coffee break if you're interested to talk a little bit more. And a little apology from me that I haven't been able to attend the full conference. I have 2 little boys at home and they didn't want me coming for the whole week. So I am here for today and for tomorrow. So thank you.
Thank you, Jennifer. Do we have any questions? The audience?
Hello. Thank you very much for your presentation. It was quite interesting, and I could say that it's beautiful. At some point, you presented the validation, the comparison between the real data from sensor C to your data from the CFD simulations. The sensor is placed in the field. So basically, when you are treating the problem from the point of view of the simulation, it's actually an effect. How do you correlate the inflow conditions in order to obtain that data? You know, because for some different boundary conditions, you're going to have another result at the anemometer point and so on.
Okay, so just that I understand your question is, how do I be sure that my inflow conditions in my model are the ones happening at the bridge?
Exactly.
So I didn't include the slide because there wasn't much time. So usually I try and run an empty box simulation where I run the flow with no bridge, and I make sure that the flow pattern that I'm expecting to see at that location is what I see. So that's what I would normally try and do. I compare this where possible with weather data collected at weather stations. So it will be an independent source of information. So it's usually bringing a number of different sources together, if that makes sense.
Okay.
I hope that answers the question. Okay.
Somehow, yes.
Yeah.
Thank you.
More questions?
Just a very simple question. Can you give us an idea of the computational time, the computational resource you need to perform this kind of simulations?
Yes. At the moment, for a RANS simulation of the full bridge, something like 10 days, but that is using a lot of parallel computing. So we have access to a large computing service funded by the state. So that helps. Yeah.
Good. Any other questions?
Hi, can you expand on the comparison that you shown, the first one for the first bridge, where you're comparing the field data with your computation? Are you specifying like the history at the inlet that you get from the field measurements, or you're comparing in time, right? For like 6 hours.
So you're asking, where do I get the information to apply at the inlet?
Oh, what type of boundary condition you specify? Like you're mapping the wind that you get from the weather stations or something like that?
Yeah, so the information for that boundary condition is coming from a weather forecasting model that was run by a colleague of mine in UCD in the meteorology department. So he runs a weather simulation like the one that we see in the weather forecast on the television. And he is able to give me the information at the location of interest for me at the same time. So the time frame that you saw on that slide in that graph was a particular time that we chose to analyze. So I said to my colleague, okay, can you tell us what wind event was happening at this part of the world at this time? And then we made sure we were comparing our results with the same time in the data in the sensor data from the bridge. Does that answer your question?
Yeah, but what is the goal of using RANs to do such a large time window in the simulation? What you're looking for to get from the RANs modeling for that particular case?
What we're hoping to achieve in a RANs, the RANs is a stepping stone. I want to get to LES. I want to see the true dynamic behavior and the changes in time. RANs is to get us to that point. It's a stepping stone. So first we need to start somewhere. We started there. So long as we are in the right ballpark with the measurements, I have confidence to keep going.
Okay, thank you.
Does that answer your question? Yeah.
Thank you.
Any more questions? Yes.
Hi, maybe just a comment to this weather forecast model.
Mm-hmm.
I think it's better than a forecast because this runs, and I think this is what you have done. This can be done with combined measurements, and so you nudge your weather forecast model with measurements, and it gets the true dynamics. So just as a comment.
Yep.
So it's much better than forecasting.
Yep. That's a very reasonable comment. Thank you.
Right. Do we have any more questions?